Hey, hey everybody, welcome back to AI and Musical Creativity. I'm Ollie Bowen and I'm chairing this next session from Sydney, Australia, where it's 7 p.m. I hope everyone's having a good time and able to join in. We're going to have 4 papers and 1 demo during this session. Any questions you want to ask, they're being placed in Slack on under the specific paper channel for each paper. So go ahead and fire off questions now or as the presentation is going. And we're going to start off with Amir Salimi and Abraham Heindel. Their paper is entitled Make Your Own Audience. Virtual listeners can filter generated drum programs. And this is going to be a live presentation. So over to you, Amir.
Make sure you unmute.
Okay, so you can see my screen, hopefully. Okay, cool. Hello, I'm Amir Salimi. I'm a master's student at the University of Alberta Computing Science Department. I'm presenting the Make Your Audience Virtual Listeners Can Filter Generated Drum Programs paper, written by me and Professor Abraham Heindel. The motivation behind this paper is that we're looking for ways to create drums virtually, and we also want these drum sounds to be interesting and unique. We want to do this with models that train fast with few examples, and we prefer quick methods of sound synthesis. Here's the approach we took. We implemented a virtual synthesizer that rapidly and randomly creates sounds. These sounds are sent to an automatic classification mechanism, or a virtual ear, that separates the sounds we want, which here are drums or percussive sounds, from sounds which we do not want. We want this mechanism to further categorize desired sounds. For example, if a sound is a drum, what type of drum is it? So let's discuss the synthesizer first. It's used to basically make noise. We use the classical digital signal processing, or DSP, to create sounds rapidly with little computational costs. And here we don't need a GPU because we're not using machine learning for sound generation. Each synthesizer has a set of noise-making units, or synthesizer modules. The outputs of the output of a synthesizer is a normalized addition of all of its modules' outputs. So each module outputs a signal. These signals are added and normalized. We wanted our approach to work with as many synthesizers as possible. So each module outputs a sound using a set of parameters that you'll find in most virtual synthesizers, or VST synthesizers, for example. Even though it's a rather simple implementation, the parameter space is quite large. I should also mention that we only use random search for this work, but in future works, we plan on using heuristic search as well. So we can randomly create sounds using this synthesizer, and I'm going to show some examples of what the output sounds like. First off, I'm going to use a synthesizer with one submodule and randomly create sounds with it. Hopefully this works. You guys can hear this? All right, so let me go through it a few times. So this is the output of one submodule. If I increase the number, I get more chaotic sounds. Right. So we can make noise, but how do we select ones that sound like drums and get rid of the rest? For that, we need a virtual ear. So we probably need a data set of drums to learn from, and we need a simpler sound representation, and we need to implement models that can learn from these representations. We curated a few different data sets of drums. FreeDB is a data set that's we provided a direct download link for. Radar.db, we provide scripts for downloading and replicating it. MixDB is a set of drums that are copyrighted, different sources, so we can't share that. And we also can make noise as needed, whenever needed. And we can use that as a database of undesired sounds. So how do we represent sounds? We mainly use Fourier transforms. And so we transform sound in 3 different ways. Frequency features is a vector of size 50 that shows the frequency content of the sound. Envelope features basically show the change in amplitude of sound for its duration. It's a vector of size 10. And spectrum features show the changes in magnitude of frequency bands over time. So for the sound, that sounds like this. You can see that it's rather chaotic in terms of frequency. The envelope is high at the start, and it gets quiet really fast. So some more examples. These are just randomly picked. Okay. I should mute it. Okay. So using these features, we implemented 2 models to learn from. TP ears, or two-phase ears, make the 2 decisions sequentially. And mixed ear models condense the spectrogram representation and make both decisions together. So this is the outline of TPE ears. So decision 1 is made, and if a certain confidence threshold is met, decision 2 is made. I trained a few very small neural networks for like 5 minutes, and I built a pipeline. So these are TPE models, and sounds are generated randomly. They're fed to the models, and if every model assigns a confidence of, I think, around 50%, the iteration stops. So it's an example of running the pipeline. So after 787 iterations, we got a sound that was accepted, and it's not too bad. I should mute. Okay. I ran this a few more times before the presentation, and I got a bunch of interesting sounds. Okay, there's around 600 more examples that we bundled with FreeDB if you're interested. And they encompass other categories like kicks and snares, and some bad examples as well. So using a pipeline similar to what you just saw, we created 250 sounds, and my co-author and I categorized the sounds, and we marked the non-percussive ones as bad, and we compared our results to what the model outputs were. And we saw that most of the sounds are percussive, but around 20% of the sounds were deemed as non-percussive by at least one of us. So that indicates a high failure rate for decision 1. So MEM models make both decisions together, and to do that by encoding the spectrogram features, and we add the envelope features to the spectrum to the encodings, and we make both decisions together. So they both use the Fourier transform features as well as the encodings. As a sanity check, we projected the encodings onto a 2D plane to see if drums of the same categories clustered together, and we saw that that was the case. And that shows that label agnostic encoding is useful for classification, at least in this case. I also implemented a interactive version of the same graph with less data points. So we see that here the synthesizer noises are marked in blue, and the ones that are further from the drum clusters are not very percussive at all. You can see the spectrogram at the bottom as well. And if we get closer to the drum clusters, the sounds get a bit more percussive. So
5 minutes to go, Amir.
okay. So there's a correlation between distance between the projections and how percussive the sounds are, but it's not a guaranteed correlation. Oops. Okay. All right, so using the embeddings as well as envelope features, we trained some models for classification of drums and also synthesizer noise. And what we saw was that adding the envelope features to the embeddings made all of our models perform better, which means that our embeddings are missing some key elements. So the envelope features are not fully captured. But still, we got pretty high accuracy. So using our best models, which in this case is this extra trees model, we built another generative pipeline similar to the TPE one that I demonstrated. And we conducted another survey, this time of 300 sounds, I believe. And what we saw was that for decision one, or whether sounds are percussive or not, there was an increase in bad examples, or there was an increase in failure rate. But for decision two, our results were comparable. But this was all done with very small encoders. So we think that with more sophisticated models for feature extraction, we can improve our results. Another benefit of this approach was that we noticed that we can train encoders purely on noise without using any drum data. So that has potential reduction of training data needed for creating a useful encoder. So to recap, we implemented a virtual synthesizer and two different types of virtual ears. We made them work together to create drum sounds. Our computational overhead was fairly small, and both approaches produce drum samples, but there's a lot of room for improvement. So in future work, we want to implement better models that also address the open set recognition problem that we've been having, and and can learn with very low data, so few-shot learning models. And we want to implement better synthesizers with a more diverse sound. And here's some links to our project code and our drum databases and some extra examples of our pipeline. That's it for this presentation. Thanks for listening. And if there's any questions, let me know.
Great, thank you very much, Amir. Thank you for keeping time. You're just within 50 minutes. So just a reminder to people listening, we have on Slack, if you found your way to the Slack, separate channels for each paper, and we've got some questions for Amir already there. So from Jason Brancazio, it's a very long question. I'm going to try and summarize a little bit. Do you think the performance of your virtual ear models could be improved by performing negative sampling with harder negatives? There's more than that. So I'll add a little bit more. Just jumping ahead. You also write that you can't quantify the novelty of the generated sounds. However, you train with autoencoders as a feature generator. Have you considered using a variational autoencoder? Because you could then look at the distance to the new sounds. Any thoughts on either of those points?
So one thing I noticed was that punishing the models more for categorizing not drums as drums isn't very useful, because that just means more iterations are needed to actually create something. And I feel like there's a lot of sounds that are being produced by the synthesizer that are percussive, but the models just don't accept them because they notice that they're made from a synthesizer. So I'm not quite sure what the best approach is. We didn't use GANs partially because there's a lot of reasons. One was because for outputting longer sounds, basically there's like a linear relationship if you're using a network to output sounds, versus with a synthesizer, you can output fairly long sounds with not much like overhead in terms of computation. And yeah, we've considered using autoencoders. We would like to implement one in the future to compare our results with, for sure.
So just further on that question, you've got that classic dilemma where you want to find, I mean, one of the uses of this, of course, is that people find original sounds that they don't get from their existing drum samples and drum machines, but you're basically using a system that tries to determine the typicality. I'm wondering if you're familiar with Graham Ritchie's work on measures of creativity, including the relationship between typicality and novelty, and whether that's something that's come up in your work. And unmute, don't forget to unmute.
I'm not familiar with that, but if you send me a link, I'll be very interested. Okay,
cool. So yeah, I think the suggestion with in the Slack comment was an interesting one. You could use, you could create an ordered latent space of the training set, then applying the encoder to the good generated samples to see how far they're drifted. And I guess there's quite a few different ways. I'm just wondering as well, further to that then, you showed that very nice user interface, very simple, but basically just a nice little audition that's in a scatter plot layout. Are you finding that, so, you know, in a situation like that, you can have a lot of duds, because as long as you've managed to reduce to a set that contains interesting and relevant solutions, then it's okay to have duds, and it's also okay to not be exhaustive covering the space. So have you got any comments on that user experience as compared to, you know, flicking through a set of presets?
Yeah, so there's a threshold at which getting rid of duds is not worth it, because you're just making your pipeline take longer to output anything. But I think right now the project is far from that threshold.
Cool. we had a couple more questions. Have you thought of a system such as yours being used in real time? Is that possible?
I think so. Like my the outputs are so fast. Like I think we can render a synthesizer with 8 stop modules in under 100 milliseconds, and that's with only one CPU process. So yeah, I think it's suitable for live usage.
So you might actually be able to set up some iterative live search.
Yeah, I think so. But yeah, it all hinges on improving the project some more.
Yeah, cool. Okay, well, thank you. That was a really fantastic presentation. Wish you the best of luck in improving that and bringing it back to this conference in the future. Next up, I think we've switched to this being a video presentation, a pre-recorded video presentation. The paper is Grigory Berliou, and the title is Interactive Learning of Microtiming in an Expressive Drum Machine. So I understand that Bob is magically behind the scenes preparing that stream. So I'm just going to say take it away and we'll see if the video starts running.
Hello everyone. My work discusses an expressive drum machine that acts on the microtiming scale. So to start with, drum machines have a history of more than 40 years now. You might know in modern commercial software such as Reason or Live, there are plugins or functions that apply groove or humanization to, let's say, a drum clip, which means kind of moving the notes around a little bit and also adapting their velocity, so how hard the notes are hit. This is done offline, and this is also done kind of out of context, so it doesn't depend on what the other instruments are doing. Meanwhile, in computer simulations of expressive musical performance, in this research field, there have been large advances made towards expressive real-time performance and also in terms of accompaniment. So taking into account what a human musician is doing in order to model the accompaniment. And I'm again looking on the micro scale. There is some stuff with drumming, but from what I've seen, it's not real time. So I found that there's kind of a niche here, and there's some really, I think, powerful research to be done, answering the question if a machine can learn to groove over a piece, so subsequent performances of a piece, by adapting to the partner's real-time input, right? So here are the design requirements that I propose. It should be, the system should be score-driven in that it should know what it has to play. So it's not a performance-driven system. It's not a jamming system necessarily. It's playing a particular scheme or song. It should be lightweight enough to be able to run it in real time and to produce timing variations in real time. It should be audio interactive, so not simply reacting to the sound, but also analyzing its own output in real time and coupling it with the input of the human musician and acting based on this coupling. It should be progressive, so learning as it goes, and scalable or transposable to other pieces or other musicians, so transferable, basically, that's what I'm thinking of here. And it should be agnostic as to the other parts of the musicians, so it should know its own part, but it doesn't need to know the exact notes that others are playing, although that is something that that we can leverage. But let's think, I'm thinking of the general situation in which either you're producing some music and you're writing some or writing down some drum lines, but maybe the other instruments are pure audio and you don't want to write them down symbolically, or it's a band situation where again you know your own part as a drummer, but you don't necessarily know have access to the other symbolic parts, right? So this is what I came up with. I call it rolypoly. It's an adaptive microtiming drum machine, and over here you see the kind of data that we're dealing with. So the input deals with every drum hit, and we use 9 general categories, so kick, snare, hi-hat, toms, crash, ride, some location and context encoding, and then very importantly the difference between the drum and the human on the last hit. So all of these refer to the previous hit, and we want to predict the correct microtiming output for the offset for the upcoming hit. So the hit that we're preparing to hit will depend on the previous hit, or rather sequence of preceding hits. So yeah, it's basically modeled as a sequence, and we want to output an offset. And to train this, we analyze every performance to produce a sequence of labels. So the labels is are y. The outputs are produced by the machine in real time is y hat. And to train it, obviously, we compare y to y hat. And how do we actually define the labels y, right? So in a traditional machine learning, supervised machine learning system, you would have a given set of labels and you would try to optimize that. In our case, there is no pre-existing data set. So as far as I could find, there is no data set that has coupled performances of a piece, multiple coupled performances of a piece. So that means, and also we want to define and to learn our own kind of synchronicity language, which means y is dependent of each performance and has to be defined post factum, right? So we don't know what the correct output of the machine would have been until after the performance. And with each subsequent performance, we're trying to get to a better, let's say, estimation of the correct y. And in this case, correct relates strongly to the particular piece that we're dealing with and the particular musician. And what I propose is to minimize the offset variance between the drum and, let's say, the guitar or whatever human instrument. So what this means is we might have an average offset between them, so they don't have to coincide directly. That's for many reasons. It might be a stylistical choice, or it might be whatever. So it might be something technical. But we want kind of around this moving average, we want the variance to be limited. We want to minimize it. And basically I came up with these ways to compute y. So just look at the green highlights. The rest is kind of scaling for variance. Basically, I'm looking at y hat, which is the generated drum offsets, and diff hat, which is the difference between the generated drum and the musician's onset. So in an, let's say, ideal world, if we minimize the diff, then y hat would be the only thing contributing to y. So that means that we've reached the correct y. The implementation is, I'm using PyTorch and Max. Max is for the audio analysis and the output. PyTorch is for parsing the MIDI part and for doing the machine learning. And I use two architecture alternatives. One is a basic two-direction LSTM. Another one is a sequence-to-sequence architecture that's inspired by the work of the Magenta team on the music VAE and the groove in those papers. They are pre-trained, so I don't start from completely random settings. I pre-trained them on the Groove MIDI dataset from Magenta, and obviously that Groove MIDI, that dataset is just solo performances, so I needed a different way to describe Y, so the Y label, which is the distance, from the drum hit to quantization. So this is basically what the user interface looks like. The video is available on YouTube. And the video goes deeper into some demonstrations and some explanations. To evaluate this, we have particular difficulties beyond just what any creative system implies. We don't have, as far as I know, benchmarks appropriate for this kind of application yet. And it's kind of hard to have a benchmark because it's very particular to the piece that you're playing and the history of performances. And even with a set history, each performance, as we've discussed, the inputs and the outputs are coupled. You can't just, for instance, use a recording of a human and apply it to different models, because the human will also reacts to the drum machine. Right, that's the way music works. So it's kind of hard to have a purely quantifiable evaluation of this. Nevertheless, I show one case in which over, let's say, 9 iterations, these are the drum guitar differences, which you can see are kind of tamed over 9 iterations. You can see the variance here is much smaller and more systematic than what it was in the baseline, and it kind of responds to the larger structure of the piece, which is also nice. A more extreme experiment I did was I did a few actually. One was inducing, let's say, swing. So we go from a more or less straight interpretation, poop, pop, poop, pop, poop, until dun, da, dun, da, dun, da, dun. So here you see they're grouped, and if we zoom in, you see. So here they were pretty straight, and after 3 iterations, we already have the dum, the dum, the dum. Right. So looking ahead, the plan is for this to be one agent, part of a multi-agent system that enables things like expressive interpretation, whether it's just of a simple MIDI part or a more complex program that involves some generation, coordination with live musical signals, self-reflection and proactivity in this coordination, and also after the performance, allowing the user to give feedback, say on you did this right, you did this wrong. Currently, the only choice that we have is whether we keep training or not, or we discard that performance. And obviously, I want time awareness. We're doing the micro scale now, but I want to go to the tempo scale, to the note, and so on, to the structure of the piece, and across performances and across different pieces also. So, as with any new research, this raises more questions than it answers, and I think the central question is this way of approaching the labeling of offsets, of desired offsets, even forget optimal, but is it musically useful, or can we find some other way? Altering the score over time might be something to try when there are systematic differences in the play. So let's something is straight, but we're playing it swung all the time, so it might make sense to alter the underlying part. Different model architectures, also yeah, trying stuff like I don't know, transformers or convolution based deep architectures, but even simpler ones I haven't really tried. Maybe something like basic multi-layer perceptron or some sort of linear or polynomial regression. Who knows? Maybe that also because it has to remain lightweight. Maybe a big elephant in the room is reinforcement learning. I don't have hands-on experience with this yet, but obviously, yeah, you're acting in an environment, you get feedback from it, depending on it, you change your policy, so it might be a good approach. I'm not sure if we have enough data or the problem is well formulated, but who knows? I'm very open to this direction. Something to check out also is one-shot learning. So we don't have data sets of multiple performances of a piece, but we do have multi-track recordings where drummers are interacting, are coupled with other musicians. Trying out other audio representations, I cite this in the paper. Also replacing onset detection because there's an entire higher order of magnitude in the onsets between guitar and drum than there is between the score and the microtiming offset. So I think there's a problem there. So we might try other kinds of control synchronization algorithms. And yeah, there's more. Mentioned there are multimodal signals as well. So coming up, what's next? I'm going to model velocity, add velocity to the model. I'm going to port it from PyTorch to a Max external using libtorch. I've already implemented it in the Max SDK, and it seems to work. I want to do a more systematic evaluation, including a more human-centered subjective evaluation, because obviously that's the whole point. And long-term, as I said, build towards a multi-scale system. So thanks a lot for your attention. I hope this was interesting to you. Check out the GitHub. There's also notebooks on there. There's also that demo video. And I'm very much open to any input or collaboration or questions or expression of interest that you might have. Thanks a lot.
One second. Okay, go.
Okay, we're back in liveness. Oh, and my apartment has become dark. We've lost the sun. Thank you very much, Greg. That was really great pre-recorded presentation. We've got a couple of questions on Slack. Nicholas Jonasson asks, why is it necessary to pre-train on Groove?
Yeah, that's a good question, and well, my intuition is basically the same as for any any transfer learning. So the point is to start from a baseline that's already halfway there. So if you're trying to get a machine drummer that kind of sounds like a drummer, you're not going to start just from something purely mechanical, but let's try to get halfway there from solo recordings of drummers and then adapt to the context. This is actually what I didn't actually try to start from a purely quantized mechanical start point. It just made sense that let's try to make it as let's try to start from a point that's already kind of dynamic in that way.
Great. And there's another question on Slack from Roger Dean. What about a desired y-hat that is a distribution of offsets from y, that is that is often what seems to be to happen in improvised groove. You'll have to interpret that.
So yeah, so I guess the distribution that we're talking about, yeah, I think that's basically the way a system like like sequence to sequence works. So you analyze and you learn over multiple performances. You basically learn the distribution of what happened or what happens in that sort of context. But yeah, the question is, the question remains, I think, what exactly are we measuring? Because if we're simply measuring, I mean, how exactly are we relating this just from the drum machine to the human, right? Because we start just with the drum machine and we go to the human. Maybe I didn't actually understand what's implied in the question.
Roger, if you I don't know if that's a clarification, not trying to achieve coincidence. I don't know if you can clarify or say whether that was a satisfactory answer, Roger. I'll just take chair's privilege and throw in a very quick question. So in the world of existing systems for a very, very, very long time, we've had this bizarre technology of groove quantize, which has just been with us for so long and is such a simple and very commonly used form of simulation. Do you think what you're doing, if it was to be put in a commercial standard like that, would it conform? Would it fit in to the groove quantized paradigm, or would it be? Is the architecture different enough that it would challenge that and require a different type of user interaction and experience?
I'm sorry. Can you please explain exactly what you mean by groove quantize?
Oh, so it's like a standard feature in digital audio workstations for MIDI, where basically you're adding expressive timing to, so the typical interface involves you having a pop-up menu of, Brazilian.
Okay. So applying a particular groove to I think it's kind of compatible with that approach, but it's obviously mine is more tuned for real time. And yeah, you can. I mean, the way basically a saved model is a model of a style, or sorry, you might call it a groove footprint or fingerprint that you can apply to a piece offline. So that can work, and it can work like as a custom groove fingerprint in that way. But again, I think the main strong point here is doing it in real time and adapting to the real input of a musician, because in all the commercial software you have presets that, oh, this is Brazilian and that's what it's going to sound no matter what the other musicians are doing, right?
Yeah, of course. So we're mindful of time. We need to move on. Roger says the answer is fine, but what he meant was being slightly apart is probably good for generating groove within distributional limits. Thanks for that input, Roger. And thank you very much, Greg, for your presentation. And moving swiftly on, we do have Jaman here. Okay, so we're not actually sure, Jaman, we're assuming that you want to have your video played. But if you want to, okay, great. So over to Bob again, and this is Jaman Ruiz, Marcos, Alistair Willis, and Robin Laney automatically calculating tonal tension, and we'll be back after the video. Thank you, Bob.
Hi everyone, my name is Germán Ruiz Marcos, and today I'm presenting a research project I have been working on together with Alistair Willis and Robin Laney at the Open University. As you can see, this project concerns the automatic calculation of tonal tension. In the literature, many authors have identified the concept of musical tension as essential to the listening experience. as a consequence, many scholars have attempted to model musical tension. These models normally study the relationship or correlation between different features and musical tension. These features can be either psychoacoustic, such as loudness, tempo changes, or onset frequency, among others, or can be cognitive features, which mainly concern melodic and harmonic motion. Models based on psychoacoustic features are made. You can probably think of different existing tools which automatically calculate loudness levels or the onset frequency of a given audio signal. On the contrary, models based on cognitive features are most of the time theoretical. We believe this lack of automated cognitive models of tension is a gap that needs to be filled, and so we have been working on this project. Taking into account we are focusing on cognitive models of tension, let me borrow Lertle's and Krumholtz's definition of tonal tension, which they describe as the sense of tension created by melodic and harmonic motion. From the existing models of tonal tension, we believe Lertle's is the most complete. And that is because of 5 reasons. First, it considers rhythmic, melodic, and harmonic components as opposed to other existing models which just focus on 1 or 2 of these components at a time. Second, it takes into account a piece's hierarchical structure as opposed to other existing models which only calculate tension following the chords in a piece of music in a sequential way. Third, it produces quantitative values of tension which are valuable for researchers in music computing like us, as we can use these values to implement new computational tools. Fourth, its components connect with all the cognitive theories, such as those of Leonard Meyer, Norm Moore, Steve Larsen's, Baruch, or Krumholtz, among others. And fifth, it has shown strong correlations against human judgments of tension. Let me briefly introduce how Lertle's model of tonal tension, or MTT, works. First, we need to select a piece of music. Then, we need to calculate its key and chord labels. Next, we need to calculate the piece's hierarchical structure. To do so, we need to use Lertle and Jackendorf's generative theory of tonal music, or GTTM. This theory consists of a collection of rules to extract the metrical components of a piece of music, its inner groups and patterns, and its hierarchical relations. Finally, we need to apply the rules in Lertle's MTT. MTT incorporates 2 different components to tonal tension. The first, harmonic tension, which in the literature is referred to as T-glob, concerns the vertical arrangement of chords and the cognitive distances between them. The second, attraction, which in the literature is referred to as alpha, concerns the horizontal arrangement of chords and the voice-leading paths between chords. To calculate the values of harmonic tension of a given piece of music, we need to calculate the cognitive distances between the chords connected by the piece's hierarchical structure. To do so, MTT relies on Lertle's tonal pitch space, or TPS, which includes a quantitative method to calculate the distance between chords in a given key that might be perceived by Western listeners. Likewise, we need to calculate a collection of surface parameters which concern 3 features: the chord's inversions, the chord's highest notes, and the role the notes in each chord play in the context of the piece's key. To calculate the values of attraction, we need to parse each of the inner melodies included in every chord transition, as well as account for the intervals within these melodies. And we need to use TPS's distance calculation again. Let me show you an example of the application of Lertle's model of tonal tension. So, MTT's first step is to pick a piece of music. Here we have the Grail theme from Wagner's Parsifal. I have chosen this piece because you can find a detailed explanation of what I'm about to say in the literature. The second step concerns the piece's harmonic analysis. As you can see at the bottom line, the theme is in the key of E-flat major, and its chord labels consist of a very common diatonic harmonic progression. Next, we move into the piece's hierarchical structure. By applying GTTM's rules on the Grail theme, one will get the tree shown on top of the picture. This tree illustrates the importance of each note with regards to the whole theme. Finally, by applying MTT's rules, one can calculate the quantitative values of harmonic tension and attraction, which are shown in the middle space. The question now is, well, is there a way of calculating these values automatically? To answer the question, let me introduce Auto10 as in automatic tonal tension, which is, in fact, the core of my talk. Auto10 is the system we have developed to automatically calculate the contributions to tonal tension of a piece of music according to Lertle's model of tonal tension. As input, Auto10 needs to be fed with a piece of music, as well as with the outputs of its GTTM analysis, all these files in music XML format. In our project, all GTTM analysis files were calculated using the interactive GTTM analyzer developed by Hamanak and colleagues, and which is publicly available. See the reference in the footnote for more detail. As output, Auto10 will produce the quantitative values of harmonic tension and attraction according to Lertle's model of tonal tension, like those we just saw in the previous slide. So how does Auto10 work? For the sake of simplicity, I'm going to indicate how the steps one needs to take to apply Lertle's model of tonal tension, those which I have already described, are implemented in Auto10. First, the piece of music to be analyzed needs to be input by the user. Second, to calculate the piece's key and chord labels, Auto10 uses the toolkit Music 21 developed by the MIT. More specifically, it uses the modules Analyze and Chordify. The hierarchical structure is another input file. However, Auto10 transforms the input GTTM tree into a matrix to ease the upcoming calculations. Recall that these GTTM-related files can be calculated by the user using the interactive GTTM analyzer. To calculate the piece's harmonic tension, we have transformed Lertle's tonal pitch space components into different objects and its rules into functions which combine different classes. In this way, Auto10 is capable of calculating the cognitive distance between chords. Likewise, the surface parameters, those concerning the chords inversions and their melodic notes, are calculated by extracting data on the pitches using Music 21 and mapping these data with the weightings defined in Lertle's MTT. Finally, to calculate the piece's values of attraction, we have represented the chords in their melodies numerically to account for every transition and their respective intervals. To evaluate Auto10, we asked ourselves the following questions. Has Lertle's MTT been correctly implemented? And how accurate are the calculations of tension provided by Auto10? Although these questions may seem pretty similar, they are looking at very different things. With the first question, we wanted to check whether we had made any mistakes when implementing Lertle's model of tonal tension computationally. We carried out 100 test cases to give an affirmative answer to the first question. However, as I do not have much time, I am not presenting these test cases in today's talk, so please refer to the paper and to Auto10's repository. With the second question, we wanted to check how accurate were Auto10's quantitative outputs compared to those calculated when manually using MTT. You may be wondering why Auto10 might not be 100% accurate, now that we have seen, after answering the first question, that it has been correctly implemented. However, it should be noted that Auto10 relies on the accuracy of the GTTM trees provided as input. Recall that we took these from the interactive GTTM analyzer, as well as on the accuracy of the chord labels, which were calculated using Music 21. As you can imagine, neither present an accuracy of 100%, and so we ask ourselves the second question. To answer this question, we have carried out 3 tests using 4 pieces of music. But why just 4 pieces of music, and why these 4? As it has already been stressed in the literature, there exists a lack of tension-related databases. In the case of Lertle's model of tonal tension, these 4 pieces are the ones that have been analyzed and studied by Lertle and Krumholz in the past. Thereby, these are the most reliable and accessible data one could find when working on Lertle's model of tonal tension. Using these data, we have carried out 3 accuracy tests. A first test to study the accuracy of the chord labels found by Auto10 compared to those in the ground truth. A second test to study the accuracy of the GTTM trees used as input in Auto10 compared to those in the ground truth. and a third test to study the correlation between Auto-10's outputs and those given by the ground truth. Again, because I have not much time, I will be only focusing on the third test. You can find more detail about the other two tests, their statistics, and more data on the paper and in Auto-10's repository. Before we get into Auto-10's evaluation, we need to discuss how Lertle's MTT was evaluated. Lertle and Krumholz recruited a group of participants and asked them to judge the degree of tension they perceive when listening to the pieces of music shown in the previous slide. As an example, this figure includes a dotted line with the average values of tension perceived by the participants when listening to the Grail theme from Wagner's Parsifal, which recall has already been introduced in this presentation. Using these data as ground truth, Lertle and Krumholz calculated a multiple regression to find the most accurate prediction of tonal tension that MTT could give. See how the predicted values of tonal tension were seen as the dependent variable, and MTT's harmonic tension and attraction as the independent variables. The results include an R-squared value as a goodness of fit measure. Between parentheses, you can find the degrees of freedom, first the number of independent variables in the regression, and second the number of events in the piece of music -2. They also calculated an adjusted value of R-squared to make it more comparable with other models for the same data that have different numbers of degrees of freedom. Likewise, they calculated the regression's coefficients, the betas, and the statistical significance given by the p-values. In this example concerning the Grail theme, we can see MTT's predictions of tonal tension, the blue line in the figure, strongly correlate with the degrees of tension perceived by human listeners and are all statistically significant. To test the accuracy of Auto-10's outputs, we have followed a similar methodology. However, in this case, the ground truth data are the predictions calculated by MTT in the previous slide, which are shown again with the blue line in this new figure. The independent variables correspond to the values of harmonic tension and attraction calculated by Auto-10. In this way, the predictions of Auto-10 that best fit MTT's ground truth are those shown by a dotted line in the figure. I will be showing the data corresponding to this multiple regression in the next slide. This slide shows the results of the previous multiple regression, the one concerning Wagner's theme, as well as the results of the rest of the pieces for similar calculations. For each piece of music, there is a value of R-squared and the degrees of freedom N and M, an adjusted value of R-squared, and the p-values corresponding to harmonic tension and attraction calculated by Auto-10. By looking at the R-squared values, that is the first column, it could be seen all regression shows strong correlation with that of Chopin, whose correlation is healthy, and are all statistically significant, as indicated by all p-values included in the last two columns. Unlike the rest of the pieces, Chopin's is constantly modulating through different keys. In fact, the prelude's last two phrases transition across 7 keys. We believe these heavy modulation processes hinder the automatic calculation of chord labels performed by Music 21, which, in turn, affect the final values of tension and could explain the lower accuracy in the case of Chopin's piece. Likewise, notice how, as the number of events increases, see Bach's and Chopin's rose, the correlation tends to decrease because there are more plausible points of deviation, as indicated by M, the second degree of freedom. In addition to the regressions shown in this slide, we also calculated other regressions to study the correlation of harmonic tension and attraction independently. Please check the paper if you are interested in these data and the respective discussions. To sum up, what is the message you should be taking home from this talk? Well, simple and easy. Auto-10 has been launched. It incorporates an automation of Lertle's theories, it is publicly available, and it has shown strong correlations against ground truth data. In future, we intend to produce a more detailed report of Auto-10's implementation. We believe the community will benefit from a thorough discussion about the computational challenges we encountered when automating Lertle's theories. Likewise, we have already started building a dataset of tonal tension based on Auto-10, which we believe can have a great impact in the community. Finally, we aim to explore the automatic generation of music with regards to tension using the doors opened by Auto-10, such as accounting for a piece's hierarchical structure. And that's it. Many thanks.
Okay, go ahead.
Okay, thank you very much, German, and I hope we have you live. Yep, you're here.
Yeah.
Turn on your video if you can. There you are. Great. Hello, welcome.
Hello.
Really interesting talk. It's been a long time since I've looked at that work. I'm just inviting people, if they want to ask any questions, go ahead and put them in the Slack under that talk, October 22nd, paper Ruiz Marcos. I just wanted to pick up on, at the very end, the final point that you want to apply this in generation, in music generation, which is, of course, the most relevant thing to this conference. And I imagine that's really not an easy thing to do. You've got maybe a very successful measure of tonal tension, but I'm guessing you can't just like use that as a fitness function in an optimization system, or plug it in as a filter. You need to kind of cleverly integrate that into some other generators. Have you had any thoughts about that, or am I
Yeah.
overcomplicating things?
Exactly. So there have been several projects in the past and also in this conference who have been focusing on generation, matching a given tension profile. So there's the Metz thesis from Daniel Brown in 2012, or Anthony Prechel's thesis from 2016, and Dorian Harriman's work with Alan Chu on Morpheus. So the thing is, I've been working on the automatic generation of music matching tension actually for the past 3 years, and hopefully I will publish all these in my thesis next year. And the thing is, we are focusing on, or I am focusing on the automatic generation, taking into account what Dorian Hermans and Ellen Chu defined as a big challenge right now, which is long-term structure. So the idea is to use the GTTM trees and the tension profiles, all that information, to generate a piece of music that takes this into account when selecting the chord transitions and the different melodic paths.
Yeah. And just out of interest, you're obviously very sensible to apply it to well understood pieces, but obviously that's a very narrow set. Why not just go and batch process it across every piece of MIDI and just sort of see what insights you might find? Or is that something that's on the cards, or something that you have done?
So the big problem here, and I think that's one of the reasons that the little series wasn't fully implemented to this moment, is that there are like lots of components and some of them are really complicated to automate. So probably the problem is getting an audio signal and trying to extract the hierarchical structure. So we have used the interactive GTTM analyzer. The problem is you need to be careful with the input signal. It has to be, you need to put the melody in just one voice and then get the rest of the content out of that. So they published another version, which was the FATA system, that could calculate the hierarchical structures for polyphonic music. However, I contacted Hamanaka because it isn't publicly available, and the group told me that it takes nearly 24 hours to track the hierarchical structure of a single piece of polyphonic music. So the big problem is you need to take with the interactive GTTM analyzer, you need to take a piece of music, you need to reorder the music, and then manually set the parameters so that you decide how the rules of GTTM are going to be weighted and applied, and then extract the information and input that into Auto 10. So the problem is that ideally we can do a lot with Auto 10 and these calculations of tension. How to think very carefully what we're going to do.
Okay, cool. And we have one question from Sandra. Is there any work that extends tension models to timbre?
So there's a really interesting paper. So in 2011, Granod and Eitan published a paper about dynamic parameters, and they analyze all these ADF acoustic features, and they do a really good literature review and explore some interesting stuff. However, I think the latest contribution is from Farwood, so far but published a quantitative model of tension in her thesis in 2012, more or less. And there's she published like this huge compendium of all the camber features that affect to tension. So probably I'll be looking at that. In my case, what I'm going to be focusing on is a little bit on how loudness might affect to timbre, and how different the different instruments and the choices you're making on the arrangement might affect on the tension perceived by the listeners.
Great. Okay. Really interesting work to follow up on. Thank you so much. And we should move on to keep track of time. And next up, we have Adrienne Foromand and Jeffrey Peters, a paper entitled Extending Deep Rhythm for Tempo and Genre Estimation Using Complex Convolutions, Multitask Learning, and Multi-Input Network, possibly the award for the longest paper title. And that's another pre-recorded video, so I'm going to assume Bob's got that queued up, and I will see you in a few minutes.
Hello everyone, I'm Adrien Fogman, and today I will present to you our work with Geoffroy Peters, which has been financed by Future Pulse project at IRCAM, named Extending Deep Rhythm for Tempo and Genre Estimation using Complex Convolutions, Multitask Learning, and Multi-Input Network. So the Deep Rhythm method has been published at ISMIR 2019. It aims to adapt an harmonic decomposition of rhythm to a deep learning formalism in order to perform two tasks: a task of global tempo estimation and a task of rhythm-oriented genre classification. To achieve this, we have developed a new representation, the harmonic constant Q modulation, that we use as an input of a deep convolutional neural network. In our new paper, we want to extend this method. We're going to see how in this presentation. We begin by presenting the deep rhythm method with this question: what is an harmonic decomposition of rhythm? According to Peters, computing the discrete Fourier transform of the onset strength function of the audio signal allows to represent the harmonic decomposition of rhythm as an harmonic series H. Here, the distance between successive beats is considered as a fundamental tempo value. To adapt this harmonic decomposition of rhythm to a deep learning formalism, we would like to use the harmonic series H as the depth of a convolutional neural network. Using the harmonic constant Q transform presented by Bittner to perform fundamental frequency estimation allows to represent and apply the lowest frequency in its range by H. The result is the HCQT, a 3D representation with a depth of H, where the superimposition allows to identify the fundamental frequency over time and its harmonics thanks to the harmonic decay induced by H. Based on these two methods, we developed a new representation that we called harmonic constant Q modulation. Here, instead of applied the discrete Fourier transform to the onset strength function, we apply directly the harmonic constant Q transform to a set of onset strength function which represent the rhythm content in several acoustic frequency bands, as in the work of Marchand with the scale transform method. On the right figure, we can see an HCQM example for a given time window, equivalent to 8 seconds. We therefore obtain a 3D representation which represents the modulation frequency, so the evolution of the frequency energy, set up to coincide with the probable global tempo. Here, the probable global tempo is around 120 BPM. We can see it in black dotted lines. H is the harmonic series or shifted coefficient and the harmonic decomposition of rhythm in B frequency bands. This representation is then used as the input of a convolutional neural network. It is followed by convolutional layers that convolve through depths, keeping the same phi b size at each layer. Filter sizes are set up to encompass several frequency bands, and we choose a large filter in phi in the last layer to take into account all the relations between various modulation frequencies that are relative to rhythm component. As output, we have a dense layer with a softmax activation function to perform classification, as in the work of Schreiber and its end-to-end tempo estimation. We use the same architecture to perform the two tasks independently. In the case of tempo estimation, we have 256 classes, and the ground truth is the global tempo value between 30 and 285 BPM. In the case of genre classification, we have n classes corresponding to n genres of the evaluated dataset. We propose 3 extensions to improve deep rhythm following music knowledge intuitions. So we want to allow to represent the interrelationships between the acoustic frequency bands. We want to gently learn the model in order to perform the two tasks simultaneously. And finally, we want to exploit the benefits of other music knowledge descriptors in addition to rhythm in order to improve classification. For the first extension, we would like to allow the model to take into account the interrelationships between the different acoustic frequency bands. To do so, we propose the use of a complex representation as input of a complex convolutional neural network. So given 2 different rhythm patterns, we can notice that for the first one, bass drum and snare are played simultaneously, and for the second one, they are played alternately. In our HCQM representation, those 2 patterns are considered the same since the HCQT of each acoustic frequency bands are computed individually. To differentiate those patterns and allow a better tempo estimation, it is important to take into account the interband relationships. To do so, we propose to maintain the phase information and so the temporal position information of the rhythm component by keeping the complex values of the HCQM instead of keeping only the modulus of the HCQM in the computation of the HCQT step. Then we stack the real and the imaginary part of the representation and use it as input of a convolutional neural network. To perform a complex convolution, we use the method of treble C, described by treble C. Given the real imaginary input representation, we convolve it with complex kernels, and the resulting filter maps have 2 parts, a real one and an imaginary one. The network is described like the original deep rhythm one by replacing the convolutional layers in the original deep rhythm by the complex convolutional layers. We keep the same output as the original deep rhythm with C equal either to the tempo classes from 30 to 286 BPM or either the genre classes. We evaluate this method according to the same protocol as for deep rhythm. For tempo estimation, we use a large-scale evaluation protocol using 3 large datasets as train sets and 7 datasets and the combination of them combined as test sets. The 3 large datasets are composed of various rhythm-oriented genres, from ballroom dances to EDM music, and also to popular music. For genre classification, to ensure a reliable evaluation, we use a tenfold cross-validation on 5 different datasets independently. In the original deep rhythm method, since the HCQM is computed on different temporal slices for a given track, used as input of the CNN, the average of the softmax prediction vectors over time is computed. We propose to compare the result of the Oracle frame prediction, meaning that we keep only the best softmax prediction vector over time according to the ground truth tempo value. It should be noted that this method is a manual selection and allows to represent the upper bound of our tempo estimation methods. So, in terms of accuracy one, the exact accuracy within a 4% window centered on the tempo ground truth, the Oracle complex deep rhythm perform better for all the datasets except for the ballroom one. However, watching the genre classification results, we can notice that there is no improvement compared to the original method. This can be explained by the fact that adding the phase information in the learning process does not allow the model to optimally generalize. Second, we want to gently learn a model to perform the two tasks simultaneously. For this, we propose a multitask learning. We perform the two tasks independently in the original deep prism method. We would like to learn the two tasks simultaneously in the same model, since we assume they are highly related. In fact, some genres are defined by the rhythm patterns played at specific tempo ranges. For this, we choose an R-parameter sharing strategy, meaning the two tasks have specific layer at the end, but the hidden layers are shared and share their parameters during the model learning. We start from the original deep prism method network. Following the R-parameter sharing strategy, we replace the output by an output dedicated to the learning of C genre classes and an output dedicated to the learning of 256 global tempo classes. We minimize the addition of the two categorical entropy losses in order to learn the model. We can therefore notice that the classic deep prism network performing the two tasks independently, there are twice more parameters than for this multitask learning network architecture. The results are displayed are the one for the tempo estimation in terms of accuracy 1, and the one for the genre classification in terms of average mean recall. The results of multitask learning and complex multitask learning are obtained using the same model, while for deep prism and complex deep prism methods, we use an independent tenfold cross-validations for both tasks. We can see that using multitask learning slightly improve tempo estimation for 3 of 4 datasets. We can also notice that for the electronic dance music dataset MTG, best results are achieved using complex multitask learning. Finally, we would like to add more information in the training than only the rhythm-based descriptor. For this, we propose to add another branch to the deep prism network. So with the original deep prism method, we perform a rhythm-based analysis using the HCQM rhythm representation as input to the deep prism network dedicated to the rhythm content analysis. So we want to improve genre classification by taking into account another descriptor that defines genres, the timbre. To do this, the solution we propose is to add another branch dedicated to timbre with a MEL spectrogram as input of a VGG-like convnet described by Choi in his work to perform large-scale automatic tagging. For this, we start again from the deep prism network. And next to it, we have the MEL spectrogram as input to a convolutional neural network. This network is based on the VGGNet architecture with convolution and max pooling operation between each layers. Finally, we concatenate the two outputs, flattened vectors, followed by a dense and a softmax layer. Here again, we have C as the genre or the tempo classes. We also evaluate an architecture multi-input, multitask with the two outputs, each one dedicated to one of the two tasks. We first present the results for tempo estimation in terms of accuracy 1. As for the precedent evaluation, the multitask methods are applied to the learning of both tasks, and for the others, we use a tenfold cross-validation protocol. We can observe that for the multi-input method, it performs better for the ballroom and the Jizan datasets, while for the multi-input multitask learning, it performs better for the extended ballroom datasets. Genre classification results are more significative since the multi-input method and its complex version perform better for all datasets. So to conclude, finally, we showed that the use of complex representation and complex convolution allow to represent the interrelationships between the acoustics frequency bands B and improve tempo estimation. The use of multitask learning allows to gently learn the model in order to perform the two tasks simultaneously and improve tempo estimation and genre classification, but only on specific datasets. And finally, the use of multi-input network allows to exploit the benefits of timbre descriptor in addition to rhythm in order to improve genre classification for all the evaluated datasets. Thanks for your attention.
Great. Thank you very much. So we have one more presentation coming up. We've got a question in, and I'm feeding back on myself, excuse me. Okay. Hello, Adrienne, and we have a couple of questions from Carl in Slack. I don't know if you've looked at those already. The first is, by adding an extra input branch, CoinNet, you report improvements. Is this because the MEL spectrogram input is an important complement, or is it due to having more model parameters overall?
So yes, okay. For this, I think the combination of the branch dedicated to timbre with the MEL spectrogram as input is improved the result. Is improving the results, since we have verified with experience. We have run some models with more parameters, more layers, and the results was not as good as with the multi-input network. And furthermore, we can also make the same remark for the complex network, since we doubled the feature maps for the complex network using the complex convolutions. And we tried to take the original network and double the feature map without complex convolutions, and the results was less good. So we assume that that there is a real improvement using the MEL spectrogram input of this timbre branch. And also we made the deeper analysis of the genre classification by observing the confusion matrices. And by observing these matrices, we can notice that the genres that are significantly influenced by the instrumentation of the timbre, in addition to the rhythm descriptor, are better classified than with the original method, with this branch with the MEL spectrogram as input. And so I think also that in the future work, maybe we could use other acoustic features to describe timbre in addition to the rhythm branch, and we choose to use this one for its simplicity. And yes, I think there is other strategies, but the idea was to really add another information to our network dedicated to rhythm.
Yeah, it's really, really interesting. And Carl also asks if complex value deep learning model, why aren't they more popular? I'm not sure if that's specifically with respect to rhythm or audio or anything. I don't know if you have any comments on that.
In the case of audio, it has already been used for instrument transcription and also for speech enhancement with a DPUNet. And I have seen some work for texture synthesis as well, since we keep the phase information.
Okay. Yeah.
But for this question, yes, I can only make some assumption. For classification tasks, I think it's not often used because maybe it's not already really known, and maybe the gain is not that high for a bigger network with more parameters. So I think it's linked with another question in this multiple question. But yeah, maybe the computation, yes, is more intensive with little benefits by applying it on other tasks that does not rely on the position of the.
But it seems, I mean, it's really essential to what you're doing, because the phase is actually, I mean, in audio tasks, the phase may or may not be important to the task, but in your case, the phase is
Yes.
super important to understanding
Sure.
the rhythm.
Yeah.
Okay, great. Thank you so much. So obviously, with all of our presenters, people can continue to ask questions in Slack, and hopefully the presenters are looking at Slack and continuing that conversation going. So please do, if you're listening or if you're tuning in later. We have one more presentation today, which is a demo, so a little bit shorter. So it's 10 minutes with including time for questions, and that's James Bradbury presenting computer-assisted corpus exploration with UMAP and agglomerative clustering. And that is also a pre-recorded video that we're going to start with, and then we'll have a little bit of time for questions at the very end of that.
Hi everyone, my name is James Bradbury. I'm a PhD student at the University of Huddersfield, and today I'm going to present a demo of computer-assisted corpus exploration with UMAP and agglomerative clustering. As a composer, my practice is centered around collecting textual-based samples into corpora and employing software to navigate through these collections in various ways to assist in the process of composition. While I like to create tools that others can use, software for me is ultimately personal, and for each artistic project it is reimagined and often created from scratch. With that in mind, this demo presents software which was used to compose an album of works, which is available at this link. The aim of this demo is to foreground the initial artistic context that called for new computer-assisted corpus exploration software, to detail the technical implementation of this software and demonstrate some of its applications to the works found in the album. Before this software was created, I'd been experimenting with the process of moshing, which involves taking raw data and representing that as a valid media format. I was doing this by walking through the file system of my laptop and converting any file into an 8-bit WAV file, by prepending a valid WAV header to the raw bytes until 5 GB of audio had been produced. More information about this open source tool can be found at the link below. This process generated a hefty amount of material, especially at that sample depth, with a variety of sounds and morphologies mostly regressing towards chaotic noise. Due to the sheer scale of the process though, inevitably in discovering and harnessing those for composition. Here are some examples from that corpus. The sounds of the corpus are all varied in length, and I wanted to segment each item into a number of recomposable chunks. Guided by listening, the kind of segmentation I was mentally performing seemed to be based on spectral changes in the sounds, rather than commonly sought strategies which might involve amplitude-based segmentation. I tried a number of algorithms for spectral segmentation, ranging in complexity, such as spectral flux and Laplacian segmentation, but nothing seemed to align with how I heard the changes. With some experimentation, I found that the fluid corpus manipulation implementation of Andrew Foote's novelty segmentation algorithm was fairly good at capturing the mental segmentation that I was doing, with a few tunable parameters to nuance the process. Every item in the corpus was processed with this algorithm to varying degrees of success. While some sounds were clearly over or under segmented, the goal wasn't to have a perfect segmentation strategy, but something that made the items of the corpus more granular and had some relationship to how I was envisaging these sounds might be broken up manually and composed with. Software produces descriptor analysis for each corpus item. I was interested in the textual qualities of the sounds and differentiating or finding similarities based on this. MFCCs were chosen for their simplicity in implementation and their potency at capturing the timbral qualities. For each corpus item, MFCCs were calculated using 40 millbands and 13 MFCC coefficients, with an FFT size of 2048 samples and a hop of 1024 samples. This produces multidimensional data for each corpus item, which is then compressed to a static vector by taking 7 statistics: the minimum, the maximum, the mean, the median, the standard deviation, the skewness, and the kurtosis. This was done to capture the morphology of each sound by representing the change in each band statistically. For each corpus item, 273 values were associated to it by flattening this information into a single dimension vector. The software then performs a dimension reduction stage using the uniform manifold approximation and projection algorithm. Unlike popular linear techniques, such as principal component analysis, UMAP is capable of representing nonlinear features of the input data in the latent space. For MFCC data and the character of the corpus sounds, this was an important consideration for creating a reduced representation that could discern between the textual characteristics, particularly for sounds where the spectrum is quite chaotic. The flat 273-point vectors were reduced to 2 dimensions, primarily to support visualization. Here you can see the position of the corpus items in the projection with various configurations of the UMAP algorithm, using the number of neighbours and minimum distance parameters. Finally, the system performs clustering on the UMAP output using an agglomerative clustering algorithm. I initially did this to evaluate the projection itself and to see how samples had been positioned in the lower dimensional space. As a way of querying that process in a more dynamic way, I ran 3 instances of clustering, asking for 250 clusters, 500 clusters, and 1600 clusters, increasing the granularity each time. At this point, I had been visualizing the UMAP projections in the browser and experimenting with manual auditioning of clusters using Max. I want to quickly touch on some applications that came out of this process, looking at the way in which the data which was created supported composition with the corpus materials. In this piece from the album, hierarchical microrhythmic structures are formed by taking clusters of impulse-based material that were discovered through auditioning the clustering results. Although the material between clusters is quite similar, the projection and the clustering are able to carve out subtle differences. Superimposing these clusters became the basis of this piece both structurally and texturally. A byproduct of the agglomerative clustering technique is a cluster containing all the items that could not be confidently grouped. Another piece was composed entirely from these samples, focusing on accenting the features of those samples found in the reject file. For another piece, the different granularities of agglomerative clustering aided the construction of material groups by auditioning 250 clusters of audio manually. It is possible to get a fairly specific understanding of what material groupings exist within the corpus without having to comb through each item. By looking at the shared membership of clusters of various clustering granularities, it is possible to surf a spectrum of perceptual tightness, kind of like exploring a tree of connected groups that are increasingly narrow in scope. In future work, I aim to develop a framework for orchestrating processes similar to those found in the software presented today. There was a lot of friction when working with the scripts and the software itself, and the workflow doesn't lend itself well to iteration and experimentation. Work has already begun at a preliminary stage on this with a new Python-based framework called Finding Things in Stuff, or FTIS. This framework has a high-level interface for composing chain-like processes of machine learning algorithms and descriptor analysis, as well as providing an interface for corpus management, filtering, and manipulation. Overall, Finding Things in Stuff makes it easier to iterate creatively by abstracting away annoying necessities such as file management while automatically documenting itself as you use it. It also has adapters for data in popular creative coding environments such as Max or Reaper, so that listening and auditioning can be rapidly introduced into the loop of moving between composing and corpus exploration.
Okay, great. Thank you very much, James. And we're back live. And that was super interesting. I particularly loved those visual representations of the data, which I didn't look at the album link, but imagining that might be the album artwork.
Something like that.
Yeah. And so we had one question online from Grig. You mentioned implementing command line interface to your process. So you're imagining live coding this, using it live?
I don't personally have a live practice, but yeah, one use case could be that it's quite a simple interface around some more complex algorithms. So you connect up different what I call analyzers. So you could have some MFCCs or a slicing algorithm, and you connect it with the bit shift operator, which I've overloaded by using a class. So that's the goal, to have a very simple interface that could be for more computer aided approaches or something live eventually in the future.
Yep. Great. And I might have missed it, but is the rationale for using sounds generated off your from files? I mean, have you tried this approach with regular audio? Is that less interesting to you, or is it less successful?
It's both, I guess. I haven't really tried it maybe with like a more traditional corpus of sounds. But for me, it was this idea of being thrown so much material that I can't make sense of it as a human. So let's have the computer do something with it and throw me back some responses and try and make sense of this corpus.
Yeah, no, that rationale makes great sense. We had a comment from Amir. It's almost a question. Any opinions on TSNE and how it compares to UMAP?
I think they're quite similar algorithms, but UMAP is quite a lot faster. And for me, the training times were getting a little bit long, and I was trying to iterate quite quickly. And then a colleague here recommended UMAP and said, "Oh, you should check this out." And I did, and I was like, "Okay, TSNE's out, UMAP's in."
There you go. Simple as that.
Yeah, that was it.
Great.
I mean, it's not super empirical. I'm usually listening and seeing what. I mean, yeah, I'm an artist, so do I like what I hear? And then I go with that.
Cool. Good. I noticed Amir is actually, of course, with us, so I don't know if you wanted to follow up with any comments. Maybe catching you by surprise there. We're a little bit over time, so I will wrap the session up there. And as I said before, I welcome everyone to continue asking questions on Slack. I welcome the presenters to keep an eye on their Slack channels to see if they've got any more questions. And we'll cut there. And I don't know if Bob needs to jump in with any announcements, but you guys all have your info on the schedule. And thank you, everybody. Good night from Sydney, and enjoy the rest of the conference.